Hello and welcome to the episode 2 of Make Your Own Damn Plugin. In the episode 1 I introduced my script to initialize your very own LV2 plugin and codebase under the Linux environment, and in this one I will discuss these basic concepts that you need to understand in DSP development, both in generalized manner and also specifically with the LV2. DSP development is one of those real-life cases when a little bit of extra attention to memory management is required, so this might be a bit heavy depending on your current programming skill level, or this might be exactly what you need to get enlightened and suddenly understand all languages much better. I'm targeting beginners here overall, including beginners with C++ programming language. Or if you have good knowledge with any other language, then you shouldn't have any issues following everything here. But let's now start with the sound. And it's a single continuous wave. Well, duh, for some, I guess. Multiple different sounds together is still a single continuous wave. So as the sound happens around you, you can represent every single thing you hear at one instance of the passing moment with a single decimal value, which is the amplitude of the sound wave at that given time. And it's called a sample. Now, if this wave would represent a sound circus when a dog is barking during an opera and someone farts loudly, at time 3.8, negative 0.6 is everything that happens. And I'm just stressing this because some people seem to think there is more magic behind sound, but there really isn't. It's really this simple. So if you take multiple samples, we can digitize the entire circus into a list of decimal values. And yes, you will always lose bits of the original sound in this process, but if you take samples frequently enough, the math says that you will only begin to lose such high frequencies a human wouldn't be able to hear anyway. The rate at which we sample the sound to this list of decimal values, it's called sample rate. Probably heard of that. You may have seen like 44.1 or 48 or 192 kilohertz sampling rates. The 48 is the most often used one, and all it means is that the sound capturing system is sampling the sound wave 48,000 times every single second. And as a side note, the math that I mentioned is actually quite simple. If you just halve the sample rate, that's the highest frequency or pitch you can get. So 48 kilohertz halved is 24 kilohertz, which is already outside human hearing rates that ends somewhere around 20 kilohertz. But that's not really as relevant as the fact that you need to have 48,000 decimal values to output 1 second of music. So if you want to create a DSP plugin that remembers 10 seconds of sound to remix it back as a delay, your plugin needs to remember all samples from the past 10 seconds. So that is then 10 seconds times, or 10 times the sample rate. And for the 48 kilohertz sampling rate, it translates into an array with almost 500,000 elements, and that's mono. So yeah, it's a big array, and as a programmer of any language, you might be tempted to say that, well, okay, yeah, there's the problem. But the amount of samples is actually not the problem here. The problem is that using just a raw array like this quickly gets quite complex in this context of audio processing. So you get tempted to use standard libraries, especially because everyone always encourages you to do so. But no matter the language, when it comes to vectors or lists or maps and dictionaries, everything that has any operations that even smell like these ones, even at best, they all work the same way when it comes to memory management, and that is slow. So we need to understand some basics about that, but warning, I'm definitely oversimplifying things. But let's take a dive into your RAM. That's where your program is loaded into when it's launched. But how big piece of RAM does it initially take? Well, it takes as much as your program knows that it needs. So at the start of your program, there is this one very slow operation of allocating that block of memory for your program in the RAM. But then accessing that memory throughout the program is as fast as it can get. If you've heard of stack memory allocation, this is it kind of oversimplified. Okay, so when doesn't your program know how much memory it needs? Well, if you think about like Notepad, obviously Notepad needs to ask for more RAM when it opens a file, reads its contents and displays it. Because that is the point when it knows how much memory is needed for that operation. So it has to ask it dynamically. And that is a heap memory allocation, oversimplified again. And like the stack allocation at the program startup, it is equally as slow operation because your RAM needs to just find and assign a space for you. And then your program just uses more RAM. And if you're using a language that manages the memory automatically, that additional allocation will be freed automatically when, for example, the file is closed. If you're using C or C++, there are keywords for both the allocating and freeing the memory, and failing to use them correctly causes crashes and memory leaks. Now, while that all might sound quite tedious and way too much information, fear not, the only key point is that all memory allocation is always slow, so you can't do any of it during real-time DSP, no matter the language you use. And all languages do it. I simply think it's the easiest to understand in C and C++ because it's straightforward how the memory is used, whereas in many other languages it might be hidden or automated for convenience, handled by interpreter or virtual machine. It's simply not possible to know what happens under the hood. Now forget all languages and just think. If you add stuff to an array or list, it gets bigger. It will need more memory to hold that stuff you added. Under the hood, your program needs to ask more room from RAM every time you call add or insert. And depending on the language, also removing or rearranging elements also potentially cause memory reallocation under the hood. And this is how it works in simple terms. In fact, in many cases, it's often possible to define array or list capacity beforehand, exactly because of this issue. But let's just keep things simple. As a rule of thumb, these keywords, operations, or partial function names, they have a very strong odor of being super duper slow due to the likely heap memory allocations happening under the hood. So, in DSP processing, you should not use them, or any libraries that could be using them, which can be a bit of a problem sometimes. If you followed the previous episode, I made a script that is basically the Hello World template of your very own real-time capable LV2 plugin. It's just like 5 simple lines in Linux terminal, and you're all set with your own plugin and code base for it. Check the link in description or probably somewhere on the screen. Anyway, once you're set, you can dive into that run function that does all of the signal processing work and start fiddling with it. But first you probably need to understand a thing or two about how the LV2 plugins work. There's a host application that is able to load your plugin, obviously, like Ardor or Kala. Now those applications have somewhere in the settings the folder or folders they scan for plugins. And while scanning, what they look for is the manifest.ttl in the subfolders, because all of the plugins are in their own folders. The manifest file is a human and machine readable file format with this really specific turtle syntax, and it defines the unique identifier for your plugin in a URI format, and the actual plugin implementation binary file to load. It can also directly define what the plugin is and what kind of properties like input and output ports it has, or it has to point to a secondary turtle file that defines those. Like here it points to the myamazingplugin.ttl with this see also notation. And here's a piece of that file on the left side. The most important parts are these port definitions. And the port defined in the turtle file must have a corresponding handler in the plugin implementation to obtain the port's pointer. And now I said that scary word, pointer. Don't overthink it. As you can see, the implementation is actually copy-paste trivial, and the same for all of these ports. The host application is just giving us some memory locations where these things are located. It could have passed us just a volume value as a simple float, but since that would be a copy of the value, then it would have to keep giving it again and again and again every single time the volume changes. Instead, it gives us the address to that original volume value, which we call a pointer. And since the value is a float type, its pointer is denoted with float star. The pointer never changes, so it can be given just once. And to check the value of the volume whenever we need, we can use the dereference operator, which is also somewhat confusingly a star. So this might be the one that makes things a bit hard to learn with C++. Let's see. Another cool thing about dereference is that we can also change the value at any given time. So for instance, if the host application paints the volume knob on the screen based on the current volume value, that knob will actually follow our changes to the value too. So pointer is just a very efficient way to share a value. So hopefully that was understandable, because I lied so that I wouldn't scare you immediately. There's actually another very important thing you need to understand about these port connections. So enable and volume here are defined as control ports. Audio in and audio out are defined as audio ports. Now audio input and audio output are value buffers. So it's not just like one value, it's actually an array of values. Yet here it's still obtained as a float pointer like the others. So what's up with that? Let's recap the volume case. It's in fact a value somewhere in the RAM, and the pointer allows us to have the shared access to that value at any given time. A base type array is similarly just values in RAM, but in C and C++ the base type array is also always a continuous block of memory. And that's very important. Because when we know it's continuous, we can just send the address of the first element, which is a float pointer. And then whoever gets that pointer can do a simple for loop over that continuous block of memory to obtain or modify those buffer values extremely efficiently. So as you can see here, the pointer can also be dereferenced with the array brackets by accessing the array elements directly. There's just one thing: how does the representative of that pointer know how many elements there are in the memory? Like here we have 4. Well, the most efficient way is to tell it when we need it. So every single time the host application wants us to process the audio buffers, it calls this run function and provides us the sample count, which is the length of those buffer arrays. So here I actually have a completely valid and simple real-time pass-through DSP algorithm. Bigger buffer means larger chunk of audio that has to fill the buffer before it can be processed by these DSP functions, which results in latency. So bigger buffer, more latency; smaller buffer, less latency. But that requires more from your CPU, because it's way more efficient to handle these big arrays than many of the small ones. This is why your audio interface or DAW has a buffer size setting. So if you have issues with latency, you just need to go smaller. If the sound starts crackling, then your computer cannot handle it, and you need to go with the higher setting and more latency, or buy a better CPU. But wait. Why do I talk about latencies when things are supposed to be real time? Well, I'm sorry to tell, but there's no such thing as real time. Get over it. But if you use buffer size of 64 with 48 kHz sampling rate, the DSP latency is 1.3 millisecond. So for reference, because sound travels 343 meters per second in air, if you take half a meter step away from your guitar amp while you are playing, you already introduce actually more latency. So that's unnoticeable, so we can call it real time. And buffer sizes go in power of 2. Below 64 is unnecessary. 64 is real time, 128 is good enough even for professionals. With 256, the drummer probably already needs to start adjusting the timing. Also fast stuff with guitar, I have noticed, becomes harder to play. 512 and above is no longer usable for live performance. However, you can also go higher if you're only mixing but not recording, as the mixing phase might actually require more from your CPU as a processing power, but then you don't have to care about the latency anymore as you are not recording. So now you understand everything about everything, and you dive into that run functions, and very soon you will notice that you need to start caching those previous samples to do anything cool with them, like remixing them to the output signal after a small delay. And that's actually exactly how delay, echo, reverb, chorus, many other plugins work. And that's when you fuck up if you skip the memory management stuff I explained before, because and there are also, decks and queues and stacks and maps, and it makes absolutely no difference what you use unless you know for sure it doesn't allocate memory when you use it the way you do. And some of these you can actually prepare with the predefined capacity and use them successfully, but it's better to stay low level for things like this. In C and C++, you can reserve that block of memory simply by using a fixed size array, and this is now a stack allocation. The other option is to do the heap allocation for the array in the active function or activate function, but that involves also other memory management responsibilities. So stack allocation is just simpler. And in other words, it means that the program knows how much memory it should reserve already at the launch. So now we have a block of memory, and if we want to remember some amount of those previously obtained samples, we really need to work within that confined array space, handling the index where we are at, and when the cache is full, then we need to start overriding old elements like a buffer that goes around and around and around, and yeah, it's called a Ringbuffer. Let's get hands-on in the next video and implement both a Ringbuffer and a simple delay plugin utilizing that. See you there. Thanks. Bye.